good morning, or good afternoon, or good evening, whenever you're listening to this. And welcome to our presentation. We are Hassan, Abubakr, and Mohammed. And in this short presentation, we will walk you through our power system load flow study using the software Power World Simulator. The main goal of this project was to investigate undervoltage conditions in a medium-sized network, and also to demonstrate how reactive power compensation, specifically shunt capacitors, can help solve them effectively. So mainly our approach was divided into two phases. Phase one, or in case one, we constructed and solved the original network to evaluate voltage performance under nominal conditions. And then in case two, we went and introduced a reactive power compensation strategy and also analyzed how that changed the system's behavior. Now, let's go step by step through modeling, analysis, and also interpretation. So here you can see the one-line diagram we worked with. The network consists of 7 buses: 1, 2, 3, 4, 5, 6, and 7. Also, it has two generators, one at bus 1, another at bus 7. Also, a series of interconnected lines and transformers. Buses 2 to 6 are load buses, each absorbing 50 MW and 30 MVAR. The generators are stepped up through delta Y grounded transformers to a 230 kV transmission level. All parameters, resistances, reactances, ratings were provided in the assignment. We carefully converted every value into per unit format based on a system base of 100 MVA and 50 Hz. Now I will be passing to my teammate Abubakr, who will be speaking about the Power World entry and also about case one. Thank you.
Assalamu alaikum and hello, doctor. My name is Abubakr, and I will be talking about case one, which is the power word entry. So, once the system base was set, we began entering the component into power word. We first created the buses, then connected the lines with their impedance values. Then the transformer were defined with proper MVA rating. Transformer 1, T1, on the left hand side is 100 MVA, and transformer 2 is 200 MVA, and the generator at bus 7 was limited to plus or minus 87 MVAR reactive capacity as specified. So, for example, here's the generator at generator 2 at bus 7. We configured the base MVA as 200 MVA and set the maximum and minimum reactive power accordingly. Similarly, T2 was entered with a reactance of 0.1 per unit and a voltage rating of 15 to 230 kV. Then we run a flat start followed by Newton-Raphson. The solver converged quickly. This is our base case 1, and we represent the system under the initial uncompensated conditions. So as shown here, the result showed that bus 7 had a voltage of 214 kV or 0.93395 per unit. This is just outside the acceptable operating range, typically plus or minus 5% of nominal, which makes it a concern. The other buses were within range and we had no overloads or no problem on the line or the transformers. T2 was carrying about 93% of its rated capacity, but we had a problem with the voltage at bus 4, so the voltage issue wasn't due to the excessive load or the transformer violation, but rather a reactive power shortage near the load end. That set the stage for our second case, which my teammate Mohammed Ammar will be talking about. So you will start.
Thank you, Abubakr. Thank you, Hassan, for the intro. Thank you,
opening mic.
Abubakr and Hassan, for the introduction and the analysis. I'll be talking about the capacitor fixing case 2. So first of all, why is bus 4 under voltage? It's if you can see in the figure, it's located downstream of a long line with a high reactance. Without enough local reactive support, it relies on the Q flow from upstream, which causes the voltage to drop. The best solution in this case is to provide the local reactive power. To fix this, we increase the existing shunt, the shunt device at bus 4. Capacitor at bus 4 originally it was set at 10 mVar. We bumped it up to 80 mVar, which is a 70 mVar increase. This addition acts like a reactive power source at the load end. After solving, again, the bus 4 voltage rose from 214 kV to 225 kV, or 0.982 per unit. Yes, here it's obvious in the table, which is a perfect 5% increase. We verified that no lines or transformers exceeded their ratings. The transformer 2 loading climbed slightly up to 91%, and generators 2 reactive output moved to around negative 55 mVar, still within the plus or minus 87 mVar limit. This before and after view, it makes the result very clear from my POV. The voltage deficit is corrected, and there were no violations that were introduced. The whole solution cost less than a tap change or a STATCOM installation would, and it's very easy to implement. I think from now, my teammate Hassan Murtada is going to be talking about the comparison and the overall summary of our project. So yeah, I'm going to be passing the mic to Hassan. Thank you all.
Hello again, Doctor. So now I'll be talking about I'll be talking about the discussion and the conclusion of our project. So raising the fixed capacitor on bus 4 from 10 to 80 mVar supplies local reactive power, reducing the reactive burden carried through transformer T2 and the 230 kV corridor. The 70 mVar increment provides an 11 kV uplift, 214 to 225, as Mohammed Ammar just mentioned, eliminating the undervoltage while lower T2 loading by roughly 3 percentage points. Sensitivity testing shows that positive or negative 10 mVar around the 80 mVar set point still maintains bus 4 within the statutory 5% band, giving operational headroom for seasonal demand variation. Now we'll be talking about the conclusion. So case one revealed bus 4 below the acceptable voltage band, though all thermal limits were satisfied. Increasing the bus 4 shunt to 80 mVar produced a 5% voltage rise to 225 kV, meeting the voltage quality requirement. Transformer line and generator reactive limits remained within specification in case 2, and the targeted reactive support at the load bus is therefore a cost-effective and technically sound solution for voltage regulation in this network. Okay, so from this study, we learned that reactive compensation is a very powerful tool when used correctly. It not only improves voltage profile, but it also reduces upstream Q demand, lowers system losses, and extends equipment life. Also, Newton-Raphson is very effective even in larger systems, as long as your model is accurate and your starting guess is reasonable. So now, just to wrap up everything, we built a 7-bus power system using per unit techniques. We identified a real undervoltage condition at bus 4, and we also solved it using a local capacitor increase from 10 to 80 mVar. All simulation files are available for review, and thank you so much for listening.
Thank you, Doctor. Thank you, Hassan.
Thank you, Doctor.